Okay.
How you doing? How you doing?
Good. Plain. I had to take organic chemistry too. I'm mad about it, but it's okay.
Why do you have to take that?
I really want to take the MCAT. And it's covered on the MCAT, so I should study it, but I really don't want to.
Okay, we're gonna go ahead and get started. So can the people on Zoom hear me and see the quiz on the screen? So could someone try, maybe you tried this, did anyone try to answer verbally? Like take yourself off mute and try. And I'm just asking because I sent a request in to see if it could get fixed.
We can hear you and see the slides.
Okay, and I can hear you now too. Okay, thank you. All right, so what we're going to do today is I want to go through quiz 4, go through the answers for quiz 4, and then we will finish up chapter 20, which is the electrochemistry stuff. And then on Tuesday, you'll have exam number 4, and that'll cover chapters 19 and 20. So it'll cover the electrochemistry stuff that we did on this last quiz, and it'll cover the electrochemistry stuff that we're finishing up today. So on Tuesday, no need to come to class, just go ahead and log into Canvas, and the exam will be on there as it has been in the past. So, okay, so quiz number 4. The first question, a reaction that is spontaneous as written. The answer is will proceed without outside intervention. Number 2, the thermodynamic quantity that expresses the extent of randomness in a system, that's entropy. I was telling the earlier class today that I don't think anyone in either class missed that question, so I was very happy about that. Number 3, which one of the following is always positive when a spontaneous process occurs? And the answer is delta S of the universe. Number 4, which one of the following processes produces a decrease of the entropy of the system? And that's dissolving oxygen in water. So in other words, you go from a gas phase to a liquid phase. Gas phase has the most entropy, most chaos. And so that was the answer for 4. Number 5, delta S is positive for, and it's that third reaction, C3H8 plus 5O2 going to 3CO2 plus 4H2O. Reason for that is you're going from 6 moles of gas to 7 moles of gas. All the others were decreases, or in the one case, it was a solid. Number 6, you're given a reaction, C2H6 going to C2H4 plus H2. And then you're given some delta H and delta S values. And then the question is really about how does the reaction relate to temperature? And so what you needed to do is remember that delta G equals delta H minus T delta S. And you needed to remember that delta G needs to be negative for it to be spontaneous. And so then you could go ahead and plug in the delta H values and delta S value that you were given, making sure you have the same units of each. And what you're basically looking to see is in that second term, the T times delta S, is there any value for T that will keep that being negative? And if you go ahead and solve it, you can see that to make it negative T would need to be greater than or equal to 1142 Kelvin. You didn't need to solve it to answer the question. You just needed to know that it's spontaneous at high temperatures. So 1142 Kelvin is a pretty high temperature. All right, number 7. What's the equilibrium constant for a reaction at 25C? And you're given the delta G value being 2.8 kilojoules per mole. So to solve this problem, you needed to remember that delta G equals minus RT times the natural log of K. You could then plug in your delta G value. But one thing you needed to do is you needed to convert that delta G value from kilojoules as it was given into joules. And so 2.8 times 10 to the third joules is equal to 2.8 kilojoules. So you need to do that conversion, then plug in your constant of 8.314 joules per Kelvin and then convert the temperature to Kelvin, 298 K, and then plug those in, and then times natural log of K. Then go ahead and then do the math and solve it, and you should get a value of 0.32. Number 8, the normal boiling point of C2CO3F3 is 47.6 degrees C. The molar enthalpy of vaporization, so that's that delta H value, delta H vaporization is 27.49 kilojoules per mole. And then the question asks, what's the change in entropy? And they want it expressed in joules per Kelvin when 28.6 grams of the material vaporizes at normal boiling point. So whenever you have molar enthalpy, then you know you're going to have to be working in moles. And so you're given a quantity in grams. And so you needed to convert that 28.6 grams into moles. So the first thing you would do is calculate the molecular weight of C2CO3F3. If you did that correctly, you should get a value of 187.35. Take the 28.6 grams and use the molecular weight to convert to moles. You get a value of 0.153 moles. So now you're set up to use the relationship of delta S equals the number of moles times delta H of vaporization divided by temperature in Kelvin. And so then it's 0.153 times 27.49. Once again, you want to convert that into joules instead of kilojoules at some point, because that's what the answer needs to be in. So I did it here, 27.49 times 10 to the third joules per mole divided by the temperature in Kelvin, which is 320.6, and you get a value of 13.1 joules per Kelvin. Number 9. For a reaction, we're given a delta H value of minus 28.1 kilojoules per mole. We're told delta G is 0 at the temperature we're working at, which is 372 Kelvin. And then we're asked to find what delta S is, and that delta S value expressed in joules per Kelvin mole. So for this problem, you wanted to use the relationship of delta G equals delta H minus T delta S. We're told delta G is 0, so we can plug that in. We're told delta H is minus 28.1 kilojoules, so we can plug that number in. And we're told the temperature is 372, so we can plug that in. Then it's just a matter of solving for delta S. If you solve for delta S, hold on here. If you solve for delta S, you get minus 0.0755 kilojoules, but the answer needed to be expressed in joules. So you needed to slide the decimal place over by 3, multiply by 1,000, and get minus 75.5 joules per Kelvin mole. And then finally, number 10. Okay, number 10, you need to calculate delta G in kilojoules per mole for this reaction. And one clue on the reaction was, you see that it says it's unbalanced in parentheses there. So, and then you're also given some delta G of formation constants to use. So the key thing was in this problem is you need to go ahead and balance that reaction. And so if you went ahead and balanced that correctly, you got 2C2H6 plus 7O2 going to 4CO2 plus 6H2O. That was important because you needed to use those coefficients in calculating your delta G value, because delta G is sum of products minus sum of reactants. And those coefficients in the balanced equation are used to multiply that times the delta G formation values that were given to you. So delta G would equal 4 times the CO2 value plus 6 times the water value, the sum of that, minus the sum of 2 times the C2H6 value and 7 times the O2 value. If you go ahead and plug in those values for those delta G of formation that we were given, you should get an answer of minus 2935 kilojoules per mole. Any questions about the quiz? Okay, so I'm going to go ahead and pull up chapter 20 slides, and then we'll go over that. Okay, so we talked a little bit about balancing redox equations in the last class, and so I want to pick up on that and continue on with, to do a couple examples. And if you recall, there's balancing redox equations when it's acidic media, and there's also basic media. So what I'd like to do is go over one of each of those, just so people are familiar with kind of the thought process that we use on that. I'm not going to do a bunch of them, I'm just going to do one of each. The others you can go and do as part of your homework and practice a little bit. I don't think it should be a surprise that there will be these on the exam on Tuesday, so please practice some. I think balancing these is pretty straightforward as long as you practice. If you don't practice, it can be a little confusing. And it's just a matter of kind of taking your time and keeping your bookkeeping straight. So let's go over a couple here. So in 2025, let's look at those problems. And there's 6 of these that they're asking you to balance. We're going to do, as I said, an acidic one and a basic one, and you guys can work on the rest. As usual, the homework answers are posted on Canvas if you get stuck. So let's look at the manganese one, which is B. So for the manganese one, we have MnO4 minus plus CH3OH going to Mn plus 2 plus HCOOH. So what we're going to do is we're going to pick out the 2 half reactions, and then we're going to balance each of those. And so let's do the manganese one first. So we have MnO4 minus going to Mn plus 2. The first thing we do with balancing these reactions is we balance the atoms that are not oxygen or hydrogen. So in this case, that would be the manganese. So we look on the left-hand side, we have 1 manganese. Look on the right-hand side, 1 manganese. Great, you don't have to do anything, we're finished with that. The next thing we would do is we would look at the oxygen. And on the left-hand side, we have NNO4 minus, so we have 4 oxygens there. And on the right-hand side, we have Mn plus 2. We don't have any oxygens there. So we're going to need to add 4 oxygens to the right-hand side of this equation. Our source of oxygen is water. So then we add 4 water molecules to the right-hand side. So there's our plus 4H2O. So now our hydrogens, or our oxygens balance, we've got 4 on each side, manganese balance, we have 1 on each side. So now what we need to do is balance our hydrogens. If we look on the left-hand side, we don't have any hydrogens when we start out. On the right-hand side, we have 4 water molecules, so 2 hydrogens in each of those for a total of 8. So we're going to need to come up with 8 hydrogen atoms on the left-hand side. And we had said before that we balance the hydrogen by adding protons, the H plus. So we'll go ahead on the left-hand side and add 8 H pluses on that side. And so now our hydrogens are balanced with 8, our oxygens are balanced, our manganese are balanced. That's all of our atoms, so we're in good shape. We kind of go back and count again to make sure everything's okay, it is. So now the other thing we have to balance is we have to balance the charge on each side of the reaction. So in other words, the charge on the left, total charge on the left has to equal the total charge on the right. So on the left, we have 1 negative charge from the NNO4. We have 8 positive charges from the 8 protons. So that's plus 8, minus 1, plus 7 on the left-hand side. On the right-hand side, we have +2 for the manganese. Water's neutral, so there's no contribution there. So we had +7 on the left side, +2 on the right side. We want to balance that. Our tool to balance the charge is adding negative electrons. So if we add 5 negative electrons on the left-hand side, then we balance out to where we have a net +2 charge on the left-hand side and a net +2 charge on the right-hand side. So now for this first half reaction, we balance the atoms, we balance the charge, and so we're good to go to the next one. But before we do that, we see that since the electrons are on the left-hand side, that this is a reduction. So this manganese is reduced. That means the manganese, since it's reduced, is an oxidizing agent, okay? And like I said, we know it's reduced because the electrons show up on the left-hand side of our equation. So let's move on to the methanol, the CH3OH, and balance that half reaction. So we have CH3OH going to HCOOH, so we have methanol going to formic acid. And so let's go ahead and first balance our carbons. Remember, we always start with the non-oxygen hydrogens. We have 1 carbon on the left from the CH3OH. We have 1 carbon on the right from the HCOOH. So once again, we don't have to do anything. The carbons are balanced. There's no other atoms except oxygen and hydrogen. So let's move on to oxygen now. On the left-hand side, we have 1 oxygen in the CH3OH. On the right-hand side, we have 2 oxygens. Those come from the HCOOH. So 2 oxygens on the right, 1 on the left. We need to have another oxygen on the left-hand side. And once again, we say that when we need to come up with an oxygen, we add water to get that oxygen. So we're going to put 1 H2O molecule on the left-hand side. And so now we have 2 oxygens on the left and 2 oxygens on the right. So we balance carbon, we balance oxygen by adding water to the left-hand side. Now we want to balance the hydrogens. So let's count those up on each side. So on the left-hand side now, we have 3 + 1, 4 coming from the CH3OH. We have 2 coming from the water. So that's 4 + 2. We have 6 on the left-hand side for hydrogen. And on the right-hand side, we have 2 hydrogens from the HCOOH, from the formic acid. So we said we had 6 on the left, we have 2 on the right. So we need to add 4 hydrogen ions to the right-hand side so that we balance out the hydrogen with 6 on each side. So now we have carbon, oxygen, and hydrogen, the atoms that are involved. We have all those balanced on the left and right-hand side of the reaction. And so now the next thing we need to do, just as we did above, is now we need to check the charge. On the left-hand side, methanol and the water, both of those are neutral. So we have a net 0 charge on that left-hand side. On the right-hand side, we have the formic acid, we have the 4 protons, the HCOOH, that's neutral, so there's no charge there. The only charge we have on the right-hand side is from the 4 H pluses. So we've got a +4 charge on the right-hand side. In order to balance that out, we can add 4 negative charge, so 4 electrons to the right-hand side. And now we have a net 0 on each side. And so the charge balances. And we expected the electrons to show up on the right-hand side here, because that means the methanol is being oxidized and thus a reducing agent. So we've always said in redox chemistry, if one thing's a reduction, the other's got to be oxidation. And since the first one was reduced, we knew this one was going to have to be oxidized. Okay, so now we've balanced our 2 half reactions. And so what we want to do now is we want to combine those 2 half reactions into our final balanced overall reaction. But before that, we have to check the charge, because when we combine these 2 reactions, we're going to have electrons on the left-hand side and electrons on the right-hand side. Those electrons need to cancel out. So whatever number of electrons we have on the left-hand side, we have to have the same number on the right-hand side so we can cancel those. Well, if we look at that first reaction, we see that the manganese reaction had 5 electrons involved. The methanol reaction, the one at the bottom, that had 4 electrons involved. So we've got a mismatch of electrons. When you have a mismatch of electrons like that, the easiest way to get a balance is to take the number of electrons in one of their half reactions and multiply the other half reaction by that number, and then vice versa. So in other words, in this first reaction, we had 5 electrons. So we're going to multiply our second reaction by 5. In the second reaction, we had 4 electrons taking place. And so we're going to multiply that first reaction by 4. So if we do that first reaction, that multiplication by 4, now we have 4 MnO4 minus, we have 32 protons, we have 20 electrons, then we have 4 Mn plus 2, and 16 waters. That second reaction, remember, we're multiplying by 5 because there were 5 electrons in that first half reaction. So if we go ahead and do that, we have 5 CH3OH, 5 water, 5 HCOOH, 20 protons, and 20 electrons. So this is good. Each of them now have 20 electrons. So those electrons are going to cancel out right side and left side when we add them up. So now that we've done that, we're going to add these two together. And we see at the very bottom here, now we get 4 MnO4 minus plus 5 CH3OH plus 12 protons going to 4 Mn plus 2, 5 HCOOH, and 11 waters. So we were able to cancel out our electrons because we had 20 electrons on the left-hand side and 20 on the right-hand side. But if you notice, there's 2 other things that we were able to do some canceling on. We're able to cancel out some of the water and some of the protons. So when you add these up, then you get same thing on the left-hand side and the right-hand side. You want to cancel those out. So for instance, we look on the left-hand side. From our first reaction, we had 32 protons on the left-hand side. And on the second reaction, we had 20 protons on the right-hand side. We can cancel out this 20 protons, the 20 H plus on the right-hand side, and cancel out 20 on the left-hand side, leaving us with those 12 H pluses on the left-hand side. We can do a similar thing with the water. The first reaction, the manganese reaction, we have 16 H2Os on the right-hand side. In the methanol reaction, the second one, we have 5 H2Os on the left-hand side. So we can cancel out 5 from each side. So now we have none on the left-hand side, and we're left with 11 on the right-hand side. So this is the process you need to follow to balance these redox type equations. You want to look at the equation you're starting with. You want to figure out which one is the reduction and which one is the oxidation. You want to balance those half reactions independently. And we do that by first looking at the non-oxygen and hydrogen atoms, balancing that in the half reaction, then using water to balance the oxygen, and then using hydrogen ions to balance the hydrogens. Once you do all that, you should have all your atoms balanced. So that's a good point to check to make sure you've got that before you move on. Then the next thing you have to do is make sure that your charge balances. And so in other words, does the total charge on the left-hand side equal the total charge on the right-hand side? For redox chemistry, it's not going to balance off starting off. You're going to have to add electrons to one side or the other. And so remember, electrons are negatively charged, and that negative charge is what we use to balance out the overall charge. Once you do all that, then double check to make sure charge and make sure atoms and all that stuff is okay for each of the individual half reactions. So you do that for the 2 half reactions, Then it comes time to combine them. The first thing you want to check when you're combining is you want to check to make sure that each have the same amount of electrons used in their half reaction. If they don't, then you need to do something like we just did here, where we multiply them by the number of electrons involved in the opposite reaction. And that's the easiest way to get that balance. Remember, you're multiplying that, in this case, 4 or 5, you're multiplying everything in the reaction, not just the electrons, but you're multiplying it by the ions and the molecules, everything. You do all that, then it's time to add the two together. The electrons should cancel out. In other words, same number of electrons on each side of the equation. And then in this case, we had an opportunity to cancel out some H plus and some H2O that showed up on both sides of it to get to our final balanced equation. Okay, any questions on this? All right, let's take a look at one. Yes. Sorry.
I understand the MnO4 going to Mn plus 2 be the oxidizing agent. I don't understand the reducing agent because it doesn't change charge. Is it just because there is no other thing for it to do?
So so you're talking about the methanol?
Yeah.
So what you could do is you could calculate out the oxidation numbers for carbon, and they're going to be different. So, and you remember that, so oxygen is typically -2, hydrogen is typically +1. And then over here, it'd be the same thing, -2, -2, +1, +1, and you can solve for your oxidation numbers. That's one way to do it. The simpler way to do it is seeing which side the electrons wind up on. Okay, so oxidation numbers are really the way you're supposed to do it. For me, the simpler way is, I know if the electrons show up on the right-hand side, this is an oxidation occurring. If the electrons are on the left-hand side of this half reaction, that's a reduction. Because remember, when we have our potentials that are given, they're always written with the electrons on the left-hand side, those are all reductions. So if it's on the right-hand side, it's oxidation. So either one of those ways you can figure out which is being oxidized, which is reducing, which is being reduced. Technically, you're supposed to fool with the oxidation numbers, but to me, that's a little pain in the neck. So I just look and say, oh, okay, the electrons wound up on the right-hand side, that must have been oxidized. Does that help? Yeah. Okay. I probably shouldn't say oxidation numbers are a pain in the neck because this is being recorded and someone will play it back and tell me why are you telling people that, but anyway. We have to delete that part. Okay, so that was one where we're in an acidic media. We also want to balance these equations when it's in a basic media. And it's very similar to the process that we just went through, but there are some subtle differences. And so I want to go through an example so you can kind of see what those differences are. But once again, I would encourage you to work a couple of the base samples to make sure that you're comfortable with doing that type of balancing. So here we have PbOH4 minus 2 plus Cl minus going to PbO2 plus Cl minus. Okay, so let's go ahead and break it into our two half reactions and balance those. So I'm going to do the left one first. So PbOH4 minus 2 going to PbO2. First thing I do is check the non-oxygen hydrogen atoms. In this case, it's lead. Pb, and I have one on the left and one on the right. So that's balanced. I don't need to do anything there. The next thing to balance is the oxygens. So I look and I see I have 4 oxygens on the left-hand side. I have 2 oxygens on the right-hand side. So I need 2 more oxygens on the right-hand side. I balance that by adding 2 water molecules. So now I've balanced my oxygens. I've got 4 on each side. Finally, I want to balance my hydrogens. I look on the left-hand side, I have 4 hydrogens there. On the right-hand side, I have 4 hydrogens. So that one's great. That one's ready to go too. So I don't need to do anything more. In this case, I don't need to add any hydrogens to either side. This is balanced. Finally, I need to balance my charge. On the left-hand side, I have a total charge of -2. On the right-hand side, both the PbO2 and water are neutral, so I have 0 there. -2 on the left-hand side, 0 on the right-hand side. If I add 2 electrons to the right-hand side to give you 2 negative charge there, now I have -2 charge on each side. Once again, because those electrons show up on the right side of this half reaction, it tells me that the lead is being oxidized. And so since it's being oxidized, it's a reducing agent. Let's look at the chlorine part of the reaction. So there we have ClO minus plus 2H plus going to Cl minus, or ClO minus going to Cl minus, ClO minus going to Cl minus. We look at the chlorine, those are balanced. So we don't have to do anything there. We've got 1 on each side. Now let's look at the oxygens. We've got 1 oxygen on the left-hand side. We can add nothing on the right-hand side, so we can add 1 water to the right-hand side. And now we've got 1 oxygen on the left, 1 oxygen on the right. Now the final thing we want to balance in terms of atoms are the hydrogen atoms. We look on the right and we have 2 hydrogen atoms from the water. We don't have any hydrogen atoms on the left. So we can balance those 2 out by adding 2 H pluses on the left. So now we balance the chlorine, the oxygen, the hydrogen. We've got all of our atoms balanced. Now we want to take a look at the charge. So on the left-hand side, we have -1 charge from the ClO minus. We have 2 positive charges from the 2 protons. So we have a net +1 on the left side there. Okay, I'm sorry, hold on. Because this is a base, we're going to first get rid of the acid. So scratch what I just said. I was thinking we were still in the acid, but we're balancing a base. So this is one of the changes between acid and base balancing. So since it's a basic media, we were told that in the problem, we're not going to have a hydrogen ion concentration. We're going to have a hydroxide ion concentration. So the way after we do the atom balancing that we get rid of the proton is for every proton we add an OH to each side. So here we have 2 H pluses. So we'll add 2 OHs to that, and that results in 2 water molecules being formed. To the right-hand side, we'll add the 2 OH minuses. And so now we're left with ClO minus plus 2 H2O going to Cl minus plus H2O plus 2 OH minus. As you can see, this leaves us with water on both sides, and this is pretty common for this. And so what we'll do is we'll cancel out the water that we can. So on the left-hand side, we had 2 waters. On the right-hand side, we had 1. So we cancel this 1 out on the right-hand side. We cancel 1 of the 2 out on the left-hand side. That leaves us with ClO minus plus water going to Cl minus plus 2 OH minus. Okay, now we can balance our charge out because we've gotten rid of those protons by adding the OH to each side. So if we do that, now we see that we have ClO minus on the left-hand side, so -1 charge. On the right-hand side, we have Cl minus and 2 OH minuses for a total of -3 charge. -1 on the left, -3 on the right. If we had 2 negative charge on the left, so in other words, 2 electrons on the left, now we have -3 on each side. And so now we balance that out. We see our electrons are on the left-hand side, so that's being that chlorine's being reduced, and thus it's an oxidizing agent. That's a good thing because with redox chemistry, if one's being oxidized, the other's going to be reduced, and so this supports that. So now we have our 2 half reactions. What we want to do now is combine the 2. And so before we combine them, we want to check and make sure our electrons are going to cancel on each side. we look on our first balanced half reaction, and that's a 2-electron process. We look at our second one, the chlorine reaction, and that's a 2-electron process also. So in this case, the electrons balance out already, so we don't have to do that multiplying by then each other's electron number to balance things out. The 2 electrons on the left, 2 electrons on the right are going to cancel. So if we go ahead, go ahead and add these up, we have our PDOH 4 minus 2 going to PDO2 plus 2 waters plus 2 electrons, and then add that to ClO minus plus H2O plus 2 electrons going to Cl minus and 2OH minus. We can then start canceling some stuff out. We see 2 electrons on the left, 2 electrons on the right, so we can cancel that. And we see, in terms of water molecules, we see 2 water molecules on the right from the first half reaction, 1 water molecule on the left from the second half reaction, and we can cancel those out, leaving us with just 1 water molecule on the right in that PDOH4 half reaction. We add all that up, and we wind up with a PDOH4 minus 2 plus ClO minus going to PDO2 plus H2O plus Cl minus plus 2OH minus. At this point, I would suggest going back and making sure in this final reaction all your atoms balance on the left and right hand side, and making sure that your charge balances on the left and right hand side. If it's a basic type reaction, you're going to have an OH minus somewhere in there. If it's an acidic media reaction, you're going to have an H plus. So similar thought process on this. Don't get confused like I did for a moment there and rush into balancing charge before I neutralize that acid. I remember we did that by adding hydroxide to each side and then converting the H plus to water. And so that's the only difference in terms of balancing acid versus base. The base one has that extra step of where you add protons and then you have to neutralize them to kind of balance stuff out. So, like I said, I can guarantee you balancing equations will be on the test on Tuesday. So please spend a little bit of time practicing some of these. Any questions on the balancing equations, either acidic or basic media? Okay. We're going to move on then to the final part of the lecture, and that's the voltaic cells. And so when you have a spontaneous redox reaction, electrons move. And so electrons are being transferred, and in this electron transfer process, you have energy being released. And that energy can do work if you have the electrons going through an external device. And so what we'll see here is we'll see some of these kind of setups, but this setup is called a voltaic cell. And as you'll see a little bit later this morning, voltaic cells, you use them every day. That's what batteries are. And so that's one reason why this is really important and people have a lot of interest in it, is the whole battery technology world. So when you create this circuit in the voltaic cell, a lot of times you'll have 2 solid metals that are connected to each other in the circuit. And these are called electrodes. And when you have electrodes, one's the anode and one is the cathode. The anode is where oxidation always occurs. The cathode is where reduction occurs. It's very important that you remember that anode is oxidation and cathode is reduction. I'll tell you how I always keep this straight is anode begins with a vowel, oxidation begins with a vowel. Cathode begins with a consonant, reduction begins with a consonant. So I always remember the vowels stick together and the consonants stick together. So if you're sitting there thinking anode, is that oxidation or reduction? Just think, oh yeah, anode has a vowel, it must be oxidation. Cathode has a consonant, begins with a consonant, must be reduction. So If you have other ways to remember it, that's fine. I'm just telling you my little trick. But the end result is you need to know anode is oxidation, cathode is reduction. If you don't know those things, you'll have a hard time with the voltaic cells. Okay, so the electrodes are typically made of some kind of conducting material, usually it's metals, and they usually don't gain or lose mass. Sometimes they do, but usually they don't. But what they do is they serve as an electron transfer surface between the electrons and the stuff that's in solution. When you start having electron flow happening in these cells, the charges in the solutions get out of balance, okay? And so the way that you get this rebalanced is there's something called a salt bridge, or there will be some type of permeable membrane that allows the ions to migrate appropriately. Here's kind of a cartoon picture on the right-hand side of a voltaic cell. And what we see here, the two long, looks like tubes, those are the electrodes. And so on the left-hand side of this figure, we have the anode. What happens at the anode? Oxidation, right? And so if oxidation is happening, then electrons are being generated. And that's what we see happening. We see electrons leaving the anode, going through our voltmeter, flowing through, this is meant to be a wire connecting these. And so the electrons flow over to the cathode. Cathode is where reduction occurs. And so if it's reduction, it needs electrons to do that reduction, right? If we just think of our redox chemistry. In the solutions down here, at the cathode, you're going to be generating anions. And at the anode, you're going to be generating cations. Because remember, at the anode, we're losing electrons. And so cathode, we're picking up electrons. And so we get those cations and anions generated. The cations are going to start wanting to migrate to balance the charge out over to the cathode. And the anions are going to go the other way. In the middle, we have that salt bridge or membrane or whatever it is that allows these to transfer. And so certain ions can go across, but we're not having all the solutions mix. That's really what that membrane or bridge is doing. So the potential difference between the anode and the cathode has two names for it. Electromotive force, EMF, or it's called the cell potential. And when it's called the cell potential, it's designated by this E with the subcell on it. Most of the time when you see stuff, people call it cell potential, but it is called EMF as well. These values are given in volts, and just remember that a volt is 1 joule per coulomb. So for a lot of these reactions, people have calculated out what the standard reduction potential is. And when I say standard reduction potential, I say what the value is when it's carried out at 1 molar concentration, 1 atmosphere pressure, and 25 degrees C. But what's interesting about these electrochemical measurements, they're not really what I would call absolute measurements. They're relative measurements. So these electrodes always have a reference that they're taken against. The most common is something called the standard hydrogen electrode, or SHE. That's the most common reference that you'll see. Any potential table that you look at, they should tell you what the reference electrode that these values are versus. SHE is the most common one, and that's the one you usually see. There is another one that's fairly common, which is standard calomel electrode, SCE. And so if it's that, they should say versus SCE. And there's some others too, but those are the two most ones that I've seen the most. Like I said, for us, all of our stuff's going to be with regards to SHE. What's significant about that is the SHE then by definition, has a value of 0. So everything's either more positive or more negative than SHE. If it's, and so if it was a different reference electrode, then that one would be 0 and things would be versus that. Here's some examples of standard reduction potentials for some different reactions. You see some here. What I want to point out is in this second, we see in the middle here, we see this 2H plus 2E going to H2. That's the standard hydrogen electrode reaction, okay, the SHE reaction. And by definition, it's 0, okay? So everything is referenced to that. And that's what I mean by these electrochemical measurements are relative measurements. They're relative to some reference electrode. In this case, the reference electrode is the SHE electrode. Okay, this is just a little more about the SHE. We can because a lot of these potentials are known for the half reactions, we can calculate potentials for the overall cell based on those values that we know. And we do that calculation by saying the cell potential is equal to the cathode potential minus the anode. Remember, cathode is oxidation, or the cathode is reduction, anode is oxidation. So we look up those potentials in the table and plug those in, and we would get cathode and anode. Cell potential is an intensive property, so that means it's independent of the amount. So in other words, the potential is the potential is what that means. Doesn't matter if you have a lot of stuff or little stuff, it still oxidizes or reduces at the same potential. Here's another example of a kind of a setup you could have. We have our anode on the left, we have our cathode on the right. In this case, the anode is a zinc metal, the cathode is copper metal on the right. We have some solutions here. And so what we're having here on the left is zinc metal being, okay, it's anode. Is that oxidation or reduction? Anode, because of the model, must be oxidation. So, and sure enough, we see our half reaction, zinc going to zinc plus 2 electrons. Those electrons are on the right. We're giving up those electrons. They're starting to flow through the wire, through the voltmeter, coming down to the copper. And then here, this copper 2 in solution is going to accept electrons that have been transferred over from the anode and reduce it down to copper plus. In this case, we actually do get some copper precipitating. It's probably going to just be in the solution. I guess there's a chance it could be on the electrode, but it's probably just going to precipitate in the solution. And so that's kind of another just view again of this voltaic cell. Okay, so if we wanted to calculate out this potential for the cell, we would use our cathode potential minus our anode potential. So we look those values up in the table or be given to us. We would have to remember which one's the cathode and which is the anode. This is why I was saying before, you got to remember anode is oxidation, cathode is reduction. And so then you would go ahead and plug those numbers in. In this case, you'd get a value of plus 1.10 volts for the potential for that cell. The more positive of the cell of the potential value, the more likely it's going to occur. Okay, so that's the takeaway on this. If that E cell is a positive, so in other words, like in the one we just did, we have an E cell value of plus 1.1. That tells me that that reaction occurs. Okay, so there is some homework associated with this. I'd like to go over a few problems just so that you can see kind of how they're worked out. But I would also suggest, though, that we'll go over a little bit, but please go and look at more of the homework questions and make sure you're comfortable doing those. So let's go ahead and look at 20.37. And in 20.37, we're going to use the standard reduction potentials, and they're in the appendix in the back of the book, Appendix E, and calculate the cell potential or the EMF for some of these reactions. So let's take a look at the first one. So we're remembering that the cell potential equals cathode minus anode. And so here's our reaction, Cl2 plus 2I minus going to Cl minus plus I2. And so let's write our half reactions for this. So we have Cl2 going to 2Cl minus, and to balance the charge, we have 2 electrons there on the left-hand side. And to be honest, when you look in that appendix, it's a pretty trivial thing to do the balancing, because what you're looking for is Cl2 gas going to Cl minus, and it'll tell you the electrons of that half reaction in the table, okay? So what we see there, the electrons are on the left-hand side, so that tells me that's a reduction, okay? So if it's a reduction, I know it's a cathode, right? Which is good because that tells me where to plug this, in this case, 1.36 value. If that's the cathode, that's the one on the left in my formula. The next one, 2I minus going to I2, 2 electrons on the right-hand side, that's an oxidation reaction. So that must be the anode if it's oxidation. Anode is that second term that I'm subtracting. So that's minus 0.54. And I did my value of 0.82 by doing that simple subtraction there. That's how you do these, calculate the standard cell potential using those individual half reduction potentials that you would get out of a table. Okay, so pretty straightforward, I think, but go ahead and practice, try a couple of them, making sure that you are comfortable doing that. Let's take a look at 20.45. So in 20.45, which we seem to have lost. There we go. 20.45, once again, we're using that data in the appendix to determine if the substances are likely to serve as an oxidant or a reductant. So the key thing to doing this problem is this first sentence, is the sentence I have written at the top. If a substance is on the left of a reduction half reaction, so in other words, in that table, it's going to be a bunch of reduction half reactions. If the substance you're interested in is on the left-hand side, it's an oxidant. It's an oxidant because it's being reduced. If it's on the right, then it's a reductant. And that's because it's being oxidized. So in this first one, Cl2 is what we're looking at. We look up Cl2 in that table, and we see that the reduction reaction is given as Cl2 plus 2E minus going to 2Cl minus. It's on the left-hand side. If it's on the left-hand side, we said it's an oxidant. The next one, NNO4 minus, and it's an acidic solution. So we look in the table, and we see that reaction is NNO4 minus, plus 8H plus 5 electrons, going to Mn plus 2 plus water. Once again, it's on the left-hand side, it's an oxidant. The third one, barium, the solid form. We see that reaction in the table is Ba plus 2 electrons going to Ba, the solid. In that case, the solid is on the right-hand side, so it's a reductant. So understanding this is pretty, once again, straightforward if you remember this sentence. If a substance on the left of a reduction half reaction, it will be an oxidant. If it's on the right, it's a reductant. Okay, now we're going to talk about doing some some calculations where we're starting to link delta G and equilibrium and things like that. And we're going to use something called the Nernst equation, which is a pretty common equation used in electrochemistry. So, but we have to get there first before we can do some examples of that. So if we have a spontaneous redox reaction, remember we said we have a positive cell potential. So in other words, this cathode minus anode value, if that E value is plus, then we have a spontaneous reaction. And this is true for all redox reactions, not just the voltaic cell ones, but it's true for everything. Remember last chapter, we talked about Gibbs free energy, delta G. And we said that delta G is what's telling us if something's spontaneous. So what that means is this positive cell potential or positive EMF has to correspond to a negative delta G. Okay, otherwise we have a conflict. Because we said last chapter that negative delta G tells us it's spontaneous. So how do they relate? Well, they relate by this relationship down at the bottom of the slide. Delta G equals minus N times F times E. F is something called the Faraday constant that has a value of 96,485 coulombs per mole. The N value is the number of moles of electrons, and then E is that cell potential or EMF value. Okay, so this Faraday's constant and number of moles allows us to relate delta G and the potential. The other thing, so we just said this minus NFE equals delta G, but recall before, last chapter, we talked about how delta G was also equal to minus RT times the natural log of K. Remember, K is that equilibrium constant. So what this allows us to do then is also we can relate NFE to the equilibrium constant. So we're starting to tie some of this stuff together from last chapter and this chapter. So let's take a look at how we can use these relationships to get to the Nernst equation. And so remember we said last chapter that delta G equals delta G naught plus RT times the natural log of Q. If we go ahead and substitute in this minus NFE, there should be a minus on this second NFE here, sorry about that. We can substitute those in for those delta G values. And then if we divide both sides by minus NF, suddenly we're left with E equals E naught minus RT divided by NF times the natural log of Q. If we get rid of the natural log and make it a base 10 log, then this introduces this 2.303 term, and now it's base 10 log of Q. If we use the standard thermodynamic temperature and then the constants of R and F, those values that we've talked about in the past, then what this works out to, and this is the version of the formula that is typically used, is we have the potential equals the standard potential minus 0.0592 divided by N. Remember, N is that number of moles of electrons times log of Q. And Q, once again, is related back to that equilibrium expression at whatever concentration you're at. Because remember, this is for non-standard conditions. That's why we're using Q. So this last equation here, that's the Nernst equation that most people are familiar with when they're talking Nernst equation and doing calculations. So we're going to do a couple examples of Nernst equation calculations, some others. But first, I want to just spend a real brief amount of time. And if you want to know more about this, you can look at it in the book. You can look at the slides in more detail. You can Google it, however you feel. But I do just want to mention, what the heck is electrochemistry good for? And really, there's several applications. Batteries is the big one. And so I want to talk about that just a little bit. And so when we talk about batteries, there's two types. There's what they call primary or secondary cells. The primary ones cannot be recharged. So based on the chemistry that's going on there, once the chemistry is exhausted, they're dead. So like those AA batteries you buy or C or D batteries you buy in the store, those are typically the primary cells. You use them when all the chemistry has been exhausted. You can't recharge them. You just have to throw them away and get some new batteries. The secondary ones can be recharged. And so that's a case of where when all the chemistry is done there, you can plug them in and then electrically recharge them and use them again. A couple other applications that we'll talk about is corrosion and ways to prevent corrosion, and then electrolysis. The most common electrolysis thing is plating metals onto metals. So the one I always think of is making chrome. If you think of chrome like on a car or something, that's an electrolysis, electroplating process. So when we talk about batteries, as I said, two that people know a lot about every day. One is the lead acid battery here on the left. That's what's in your car, or at least in most cars. And so if you have a regular gasoline type car, I guarantee you have a lead acid battery. Because there is lead in there, okay, a lot of lead in there, and there's always a really strong acid in there. That's why if your battery is finished, if it's dead, you really want to dispose of it properly, because lead's a bad metal for pollution. Acids are bad. You don't want to get that on you. It's pretty strong acid. So that's why with those car batteries, it's really good to recycle those properly. The alkaline battery on the right, that's less harmful or less severe chemicals in those. That's why those typically are just thrown in the trash. The recyclable ones, you tend to need to recycle. I mean, the rechargeable ones, you want to recycle those just because of some of the materials in there are a little nasty. There's something called fuel cells. Fuel cells technically are not batteries. The one you hear most about are hydrogen fuel cells, where you use electrochemistry to react hydrogen and oxygen to form water. And when that reaction happens, you get some energy produced, you get electrons moving. Corrosion, most people don't think of it as corrosion, they think of it as rust. So that orange stuff that you see forming on metal, that's rust. That's iron oxide being formed. So that's this Fe2O3. There's almost always moisture involved in that reaction. And so sometimes it's water, but sometimes it's just humidity, so water from the air. But you got to have water in that reaction. And then there you see the chemistry on it if you're interested. You can do some things to prevent corrosion. We're not going to get into that. But I do just want to mention electrolysis. And so electrolysis is when you put electricity into it to drive a particular chemical reaction that's not spontaneous, that doesn't want to go. And so you can, by putting electricity into it, drive that reaction. And like I said, electroplating is the one that I think most people think of when they think of electrolysis, where you have some type of metal object, steel object in this case, and they're plating nickel onto it. Like I said, chrome is one that I think of, because you hear about people electroplating metals to make chrome. So those are just some examples of electrochemistry in our day-to-day life that I just wanted to mention to you. We've got a few more minutes left. What I want to do is just quickly go through a couple of homework problems. And so please spend some time working on these because this is the kind of stuff that you're likely to see on the exam on Tuesday. The first one, 2051, we're given a series of half reactions, and then we want to write a balanced equation for the oxidation of Fe plus 2 by S2O6 minus 2. So we were given those half reactions. We're told that the iron's being oxidized. If the iron's being oxidized, then we know the electron's going to be on the right-hand side of the half reaction. So we have Fe plus 2 going to Fe plus 3 plus 1 electron. Our other reaction, our reduction part of the reaction is S2O6 minus 2 plus 4H plus 2E going to 2H2SO4. Well, we see right off the bat, we've got an imbalance of electrons. Okay, so we've got 1 electron in that first reaction, 2 electrons in the second. We need to have those electrons balanced because when we get to our final reaction, we want the electrons to cancel out on the two sides of the reaction. So we'll multiply that first one by 2, resulting in 2 Fe plus 2, going to 2 Fe plus 3 plus 2 electrons. And now we can go ahead and add these two up. If we add those up, we get a final reaction of 2 Fe plus 2 plus S2O6 minus 2 plus 4 protons, going to 2 Fe plus 3 and 2 sulfuric acid. So we could go ahead and double check our atoms and our charge and everything, but that should all balance. But what we learned from this is we learned that first, that's the iron reaction, that's an oxidation. If it's oxidation, it's the anode. And then the second one is a reduction. So if it's reduction, it's cathode. We want to find our cell potential. It's cathode minus anode, right? So then that gives us our 0.60 minus 0.77 equals 0.17. And so then you could go ahead and follow a similar process with the other two problems here. And once again, just like normal, the homework is posted on Canvas as you're working through if you get stuck on something. And then of course the answers are in the back of your book also. The second part of the problem is calculate the delta G for the reaction at 298 Kelvin. So here the key is remembering that delta G equals minus N times F times E naught. We just calculated E in the first part of the problem, so we know that value. F is that Faraday's constant, 96,485, so we can plug that in. N is that number of moles. Remember, we said that was 2 moles of electrons. So we know that. We can plug all those numbers in, and we can calculate our value as comes out to be 3.3 times 10 to the 4th joules. So the key here is knowing that's the formula we want to use. And then in part C, we wanted to calculate the equilibrium constant, K. And so that's where our relationship of delta G equals minus RT natural log of K comes into play. We just calculated our delta G value, that's that 3.3 times 10 to the 4th. We have our constant, R in this case is 8.314, temperature is 298 K. Then we can solve for K because then we have natural log of K there, and we can do that now. So take a look at those 3 formulas that we use there to do that calculation. Let's look at 57. So in 57, we're told we have a standard cell potential of 0.177 at 298 K. And I want to know the value of the equilibrium constant for different numbers of moles of electrons. So we use that formula at the top there, E equals RT over NF times the natural log of K. So we're going to be solving for that K value. We know what our potential is. We're given that information. We know the temperature. We know the R value, we know what F is. We've got all that stuff, we simply plug all that in. In this first case, we're saying the number of moles of electrons is 1, so that's where the 1 value comes from. In the subsequent ones, we do 2 and 3. But then we go ahead and do that, solve that problem, and we get 982. What I want to point out to you on this problem is, so the only thing we're changing is the number of moles of electrons. So the first one, with 1 mole of electron, we get a value of 982 for the equilibrium constant. We go to 2 moles, now we're at 9.85 times 10 to the 5th. We go to the 3, and now it's 9.77 times 10 to the 8th. Boy, that really jumps up, doesn't it? So it's pretty interesting to see how just that difference in moles of electrons made a huge difference in what that equilibrium constant was. And so if that equilibrium constant is getting really big, what does that tell us? It tells us that reaction is really going. Remember, that's products over reactants. Okay, let's look at 65. So in 65, we have a voltaic cell and we're given the reaction for it. And we want to find the cell potential under standard conditions and then cell potential under non-standard conditions. If you hear cell potential, non-standard conditions, the thing that should pop into your head is Nernst equation, okay? If it's cell potential with standard conditions, it's this simple cathode minus anode. If it's cell potential at non-standard conditions, then you're going to be using the Nernst equation, okay? So just try and remember that. So there's our equation, our reaction up there. We break it into the half reactions so we can figure out which one is being oxidized and which one's being reduced. The one that's being oxidized is happening at the anode. The one that's being reduced is happening at the cathode. That allows us to plug the potentials in to cathode minus anode and get our standard cell potential, which in this case is 0.48. Now, as I said, Nernst equation is what we use for non-standard conditions. So once again, here's our little path down to the Nernst equation. But this formula that has a little star by it is the one we're interested in, where the potential at non-standard conditions equals the standard potential minus 0.0592 divided by N. That N is the number of moles of electrons. In this case, we look back to our equation, we see that N value is going to be 2 because this is the 2 electron reaction. And then we have log of Q. Q is products over reactants. We go back to our equation up top, then we see nickel on the right-hand side and zinc on the left-hand side. Those are solids, so those are going to be 1, so they don't show up in our expression. Zinc plus 2, product will be the numerator, that concentration. Nickel plus 2, reactant concentration will be the denominator. And sure enough, here's our Q expression, zinc plus 2 divided by Ni plus 2. And zinc ion concentration was 0.1 molar, nickel ion concentration 3 molar. We plug those into this. So we plug in our 0.48 value that we calculated up front for that standard cell potential. We plug in our 2 moles of electrons, and we plug in our concentrations, and then it's a matter of solving that problem. Okay? So once again, standard cathode minus anode, non-standard Nernst equation. Okay, let's take a look at one more. This is 67. 67 is very similar to 65. So try that on your own. We're kind of running out of time here. Try that on your own and try the other homework problems. So just to review for a second. Tuesday we'll have the exam covering chapter 17 and 19. 19 and 20, sorry about that. 19, people did pretty well in the quiz, so congratulations, that was good to see. So that should be fresh in your mind, review some of that stuff. And then chapter 20 is the electrochemistry stuff. So I guarantee you balancing equations is going to be in there. I guarantee you something with like Nernst equation type calculations going to be in there. So make sure you're comfortable with these calculations and the balancing stuff. And especially with the balancing, the only way I can tell you to kind of get comfortable with that is to just work some of these and make sure that you get used to the kind of bookkeeping you got to do to keep it straight. So Tuesday, the test will be online on Canvas. So just log in during the class period and take the test. And then I'll see you all again on Thursday. And then on Thursday, we'll start chapter, I think 24 it is, which is kind of like an intro to organic chemistry. So any questions before we end? Okay, all right, thank you. And see you Thursday.